Hello friends, thanks for joining me. This is the first video of a series where we will be going through the excellent book on quantum mechanics by Steven Weinberg. Although much of the material we will be presenting here are based on this book, we feel that some parts of it requires more extensive explanations in order for this to be suitable as a first course. As a result, much more materials will be discussed here compared with the book, making this a rather lengthy treatment. We hope our more advanced viewers will bear this with patience. This is especially necessary for the first few chapters, since this is where the foundation of our understanding of quantum mechanics is built. So we shall go through these slowly to build up confidence and familiarity with the subject. Many examples will be provided for this purpose. This series will proceed from the basics all the way to the advanced, reaching the levels of typical graduate courses in quantum mechanics. Before we begin, let me make a comment on the order in which we will be reading the book. In my opinion, for pedagogical reasons, for the first 3 chapters, we should read chapter 3, then 2, followed by 1. The rationale is that we can learn the basic rules of quantum mechanics in its modern and complete formulation, starting in chapter 3, where the general principles of quantum mechanics is introduced. Then we move on to chapter 2, where we go through some important examples, doing actual calculations on particle states in a central potential, to gain some experience on how the rules in chapter 3 are used. After we have gained some familiarity about the formalism and mathematics of quantum mechanics, now armed with the benefits of hindsight, we can then better appreciate the foresight of the great physicists who discovered quantum mechanics from experimental data during the early days of the 20th century, and understand what motivates the creation of the rules formulated in chapter 3. This is the historical introduction of quantum mechanics in chapter 1. Now without further ado, let's begin. Quantum mechanics was born in 1925, when Heisenberg postulated in his groundbreaking paper that the quantum world, which at the time is the realm of particles such as molecules, atoms, and electrons, needs a totally different kinematics from those that are applicable in the familiar classical world of macroscopic objects. In classical mechanics, while it is entirely appropriate to speak of the trajectories of a point particle as it travels through space and time, an xt could properly describe its state, Heisenberg realized that one could not describe the behavior of an electron around an atom this way. You simply could not get the results observed in the spectral lines emitted by atoms using such a description. Therefore, a new quantum kinematics need to be invented for the electron. In physics, the kinematics of a system is a set of variables that completely describes the state of a system at any given moment. For example, the position vector in time completely describes a point particle in classical physics. In quantum mechanics, the particle state is given by a very different sort of vector, with a radically different interpretation. We call these state vectors. Although very different, these state vectors share such similar mathematical properties with the vectors that we are familiar with in classical mechanics, that much of what we know in 3D vector analysis still hold true. We can make full use of this to learn about quantum states by simply introducing a change of notation and noting the differences where they occur. Let's make a dictionary to relate what we know about 3D vectors to the new state vectors in quantum mechanics. On the left is the 3D vector familiar in classical mechanics. On the right, we have the state vector in quantum mechanics, where Dirac's bracket notation is introduced. Here, vectors are represented by right-pointing angle brackets, known as Kets. All vectors that live in the space of 3D vectors can be represented as linear combinations of some basis vectors. In the same way, there exist basis vectors for the space of state vectors as well. For 3D vectors, all components that enter into any linear combinations of vectors are all real numbers. Hence, the space of all 3D vectors is known as a real vector space. On the other hand, the components that appear in any linear combinations of vectors in the space of state vectors could be complex numbers, and therefore state vectors live in a complex vector space. As is well known in vector analysis, basis vectors are not unique, and we can always find a basis which elements satisfy the orthonormality conditions. For 3D vectors, this is a condition on the dot product, which maps two basis elements to a real number. Orthogonal means the dot product of two elements must give 0, while a vector is normalized if the dot product with itself is equal to 1. Similarly, an orthonormal basis can also be found in the space of state vectors, but with an inner product that is slightly different from the dot product. To better understand the inner product of state vectors, we need to introduce the concept of a dual vector. A dual vector is denoted by a left-pointing bracket in Dirac's notation, and is known as a bra. A dual vector is defined by the Hermitian conjugate of a vector. In a given basis, Hermitian conjugation replaces the basis elements with their corresponding bra, while taking complex conjugation on all vector components. You may ask, what then are the duals of the basis elements? This question is best answered with an example. Suppose we have another vector in the same basis. Taking the inner product of this new vector W with the vector V, we get where the last equality is due to the orthonormal property of the basis vectors. Now we can see that as long as the inner products between basis elements are defined, we will be able to evaluate the inner products between all state vectors. So the dual of a basis element is essentially defined through its inner product with the basis vectors. Once we have chosen an orthonormal basis, it is often convenient to represent state vectors as matrices, as is commonly done with 3D vectors. The ket is represented by a column vector, while its dual, the bra, is represented by a row vector with all its entries complex conjugated. The inner product is then obtained by contracting row with column, similar to the dot product, but taking complex conjugation on the row. This last expression for the inner product allows us to prove an important property. The inner product of state vectors W with V is equal to the complex conjugation of the inner product with the arguments exchanged. We now introduce a useful notation. The linear combination of two vectors V and V' is denoted by a resulting ket. This linearity is indicated by the label or argument of the ket. Alpha and alpha prime are arbitrary complex numbers. If we take the Hermitian conjugation of this ket, the result is given by the Hermitian conjugate of the linear combination on the left-hand side. Thus we conclude that the ket is linear with respect to its argument, while the bra is anti-linear. Anti-linear means that complex conjugation is taken with the coefficients alpha and alpha prime. These lead directly to the sesquilinear nature of the state space inner product. Sesqui means 1.5, as the inner product is fully linear in its right argument, while anti-linear in its left argument, which is sort of like a half linear. Now is the time to explain what state vectors really mean. Let's work with the example of a 3D quantum system. 3D means that the states of the system can all be represented by the linear combinations of three basis elements. 3D here does not refer to the number of spatial dimensions, but rather is the maximum number of possible outcomes one can get from the measurement of some observable of the system. In quantum mechanics, an observable refers to any variable describing a physical system that could be measured or observed. Each unique observable is associated with a unique set of basis elements. We label the observable in this example as A. Each basis element represents a possible outcome when we measure an observable of the system. The process of measuring an observable A of a quantum state V goes as follows. The state V before measurement can be expressed in terms of the basis states associated with A. After measurement, one of the possible values A1, A2, or A3 is obtained. Each of these values occurs with the probability given by the absolute square of the corresponding alpha. The system then ends up in one of the states that corresponds to the measured value A. This highlights the key feature of quantum mechanics, that the outcomes of measurements done on quantum systems can only be predicted up to probabilities, even when the initial state of the system is completely known. This is the fundamental uncertainty of the quantum theory that exists even when we have the complete description of the state of the system, and is an important postulate of the theory. Here are some examples of quantum states. The state of a quantum coin. It is expressed in the basis associated with an observable that carries information on the possible values of the coin that could face up. The state of a quantum dice, in the basis that encodes the side of the dice facing up. The famous Schrodinger's cat, in a state that carries information about its vitality. It is important to note that all these systems are still in some indeterminate states with regards to the observables that are to be measured. These states can only tell us the probabilities of the various outcomes that are only actualized upon measurement. Let's now talk about the probabilities of measurement outcomes. Instead of the previous example of a three-state system, we generalize our discussion to an n-state system in which all measurements yield only the maximum number of n outcomes. Psi is the state vector which now describes an n-state quantum system. It is expressed in a basis which corresponds to some observable A. And just as we learned in vector analysis, there are infinitely many bases with which a vector could be represented. For a state vector, different bases represents different observables which are measurable on a quantum state. Each representation of a state vector tells us what happens when we measure any observable of a quantum system. If the system is in state psi, and we wish to measure observable A, recall that the basis associated with A satisfies the autonormality condition. This implies that when I is not equal to J, the inner product of the states AI and AJ, which is also called the overlap of the two states, is equal to 0. When this happens, we say that these states are distinct. Distinct here is to be understood in the same sense of the outcomes being mutually exclusive, as familiar in probability theory. The probability of getting the outcome AI after measuring A is given by, which is equal to the absolute square of the inner product between psi and AI. This can be seen by calculating the probability amplitude of the process directly and using the orthonormal condition of the basis. In general, the probability of an outcome is equal to the absolute square of the corresponding amplitude. In order for this expression to be a probability, it has to be positive. This is guaranteed by the absolute square. The probabilities of all outcomes must also sum to 1. This imposes a condition on the state vector. Note that the sum of all alphas is equal to the inner product of psi with itself. This is easily seen by applying the orthonormal conditions in the A basis. It is also known as the squared norm of a vector, while the norm itself is just the square root of this and can be interpreted as the length of the vector. Thus, the requirement on the sum of all probabilities being 1 corresponds to the condition that state vectors must normalize to 1. This is also known as the normalization condition. But how do we normalize state vectors? Here we make an important claim. State vectors that are proportional to each other are physically equivalent. That is to say, if psi tilde is equal to some constant times psi, this implies that they are physically equivalent. This can be seen in the following way. Suppose we measure an arbitrary observable A on the state psi tilde and look at the relative probabilities of the outcomes. We find that the proportionality factor cancels, and the result is equal to that of psi. Since the sole purpose of the state vector is to carry the total statistical information about the system, this shows that psi tilde and psi are equivalent. Conventionally, we say that both vectors belong to the same ray. To normalize a state vector, we first note that the squared norm of any vector is greater or equal to 0. This is due to it being the sum of the absolute square of its components. The equal sign holds only when psi is a null vector. Recall that the null vector has all 0 components in any basis. Therefore, a state vector cannot be a null vector. So the squared norm of any state vector must be greater than 0. To normalize psi, we shall replace it with an equivalent psi tilde. The normalization factor n is given by the inverse of the norm, so it is well defined only if psi is not the null vector. This implies that psi tilde is now normalized. From here on, unless otherwise stated, all state vectors are taken to be normalized. The state vectors of a quantum system live in a complex Hilbert space. We denote this space by the curly h. An operation of vector addition exists in the Hilbert space, such that the vector that resulted from the addition of two vectors is also contained in the Hilbert space. There is also scalar multiplication, such that multiplying a vector in the Hilbert space by a complex number returns another vector within the same space. These two properties imply that the Hilbert space is a complex vector space. Finally, what makes a Hilbert space is that it possesses a sesquilinear inner product. This inner product maps any two vectors in a complex Hilbert space to a complex number. We have already talked about the properties of the sesquilinear inner product. Let's summarize. The first two properties state that the inner product is linear in the first argument and antilinear in the second argument, hence sesquilinear. The third says that vectors in the Hilbert space that are not null are state vectors. We now introduce the concept of operators. An operator acts on a vector in a vector space to give another vector in a target vector space. It is a linear map. Of course, the target vector space can be the same as the original vector space. For our purpose, We are interested in operators that maps vectors on a Hilbert space to other vectors on the same Hilbert space. A useful representation of an operator is a matrix, since a vector can be represented as a column. The operator, which is a linear operation on vectors, can therefore be represented by a matrix, which is a linear operation on columns. I will explain how to construct a matrix corresponding to a given operator shortly. Now let's look at some examples of operators relevant to quantum mechanics. Consider a state psi expressed in a basis associated with some observable. In the last equality, we have used the fact that the component alpha I is equal to the inner product between the basis element AI and psi, due to the autonormality condition. The terms indexed by I can then be collected into a sum. This term in the square bracket is an example of an operator acting in the Hilbert space. It maps any vector psi in the Hilbert space onto itself. Hence it is called the identity operator. Note that this applies to any basis that satisfies the autonormality condition. Hence the identity operator can have as many different representations as there are bases. This relation between the identity operator and a vector basis is called the completeness relation. It represents the fact that any vector in the vector space can be expressed in terms of the basis elements. Each element in the sum is itself an operator. We call this a projector or a projection operator. The projector associated with AI projects out the component of psi that is parallel to AI and eliminates all orthogonal components. If psi is already proportional to AI, it is then left unchanged. This configuration of an operator is called a Ket-bra for obvious reason. Weinberg calls this a diet. In general, the ket and bra need not be from the same state. The projector appears in the calculations of probabilities of outcomes, as can be seen from a previous expression. It is often denoted by P, with the state that it is projecting out indicated in its argument. The expression where an operator is sandwiched between the bra and ket of a state vector is called the expectation value of the operator. It is the expectation value associated with a given state. We will show why this makes sense in a minute. In general, besides projecting out just a vector, one could also project an entire subspace. This involves the sum of projectors corresponding to a subbasis. By definition, all vectors belonging to the subspace can be expressed in terms of this subbasis. Here we introduce the concept of the span of a set of vectors. The span of the subbasis is defined by the complete set of vectors formed out of all possible linear combinations of subbasis elements. This precisely defines our subspace V. The projector into V is denoted by PV. PAI is therefore a special case of a projector into a one-dimensional subspace. Let's look at some properties of projectors. Suppose PV projects into a subspace V. Let psi be any state vector. In general, part of this vector will be inside V, while the rest outside V, or in other words, orthogonal to V. Applying PV to psi, the part orthogonal to V will be removed, leaving just the part in V. Using the orthonormality condition satisfied by the basis in V, we find that the part of psi within V is left unchanged. Applying PV again will not change this expression. And because psi is arbitrary, we conclude that applying a projector to itself will give us the same projector. This is in fact the definition of a projector, and also implies that its action on a vector within V is equivalent to identity. Another obvious result that follows would be, where the blue projector projects into any subspace that is orthogonal to V, consecutive applications of the two projectors have to be zero, because the two subspaces are disjoint, and therefore share no common vector, which could have survived both projections. We now introduce an important type of operators called Hermitian Operators. Practically all physical observables we encounter are Hermitian operators. But let's first introduce the concept of the Hermitian conjugation of an operator. First, let an operator O act on a state psi. Then take the inner product of the resulting state with another state phi. By definition, this inner product is equal to the bra of the Hermitian conjugate of O, acting on the phi, contracted with ket psi. The Hermitian conjugation is denoted by the dagger superscript. Recall that a bra is the Hermitian conjugation of a ket. O is a Hermitian operator if it is equal to its own Hermitian conjugate. To avoid any confusion, let me repeat. This relation holds for any operator and is the definition of operator Hermitian conjugation. In general, one can shift an operator from the ket side to the bra side and vice versa by replacing an operator with its Hermitian conjugate, while the relation holds only for Hermitian operators. One can shift a Hermitian operator from ket side to bra side at will. We will now show that physical observables are Hermitian operators. Recall that an observable A is defined by a vector basis where each element corresponds to a possible measurement outcome. For each outcome, one gets a measured value, which is a real number. Thus, when given a state psi, the expectation value of A can be calculated like so, which is the product of the measured value with its probability, summed over all possible outcomes. The probability of an outcome is given by the absolute square of the component of psi associated with it. This expression can be written as, if we collect all the terms related to the measured outcomes and values in the middle, we find the form previously referred to as the expectation value of an operator. Therefore, it is reasonable to define this term, isolated from the state of the system psi, as the operator representing the observable A. We can show that this operator is Hermitian. First, let A act on psi on the ket side of the inner product between vectors phi and psi. Using the above representation, this is, the bra of A acting on phi is given by the Hermitian conjugate of the corresponding ket. Using again the representation of A, we have, since the AIs are real, and using the sesquilinear property of the inner products, followed by taking the inner product with ket psi gives. This shows that we can move A from the ket side of the inner product to the bra side, and therefore the operator A is Hermitian. However, this is not the only operator that could be connected with observable A. The basis that defines A is connected with a set of measured values, but it may also be mapped into many others by an arbitrary function, f. F can therefore map the operator A into Fa, which is simply defined by replacing the values Ai by Fai. The function of an operator can be formally defined by its power series. Notice that we can evaluate a power of A by just raising the AI's to the same power. This is most easily seen by the example of A squared, where the orthonormal properties of the bases can be used to get the result. The expectation value of FA can similarly be obtained by simply replacing AI by FAI, which is equivalent to substituting operator FA in place of A. It is worthwhile to review what goes on when we measure observable A. If the system is in an initial state psi, after measurement, the system is found to be in state AI with a probability prescribed by quantum mechanics. We get from this measurement a reading of either AI or some other values related to it by some function f. The sort of readings we get depends on the experimental setup. For example, a computer may process the raw data to give some other well-defined output. The key point is that the output values allow us to deduce that the system is now in the post-measurement state AI. This is the typical schematics for measuring an observable of a quantum system. Let's explore the notion of operators as Ket-bras in a more general way. An operator is completely defined by its actions on all the vectors in the Hilbert space. In fact, we only have to specify the actions of an operator on all the elements of an arbitrary basis to know how it will act on any vector. This is due to the linearity in the way operators act. A here is not assumed to be Hermitian. The output vectors v tildes may not be a basis and could in general be any set of vectors which need not even be unique. Without loss of generality, we can define A by its action on some orthonormal basis. From this definition, we could immediately construct a Ket-bra representation of A. One can easily check that this representation gives the correct rules for mapping the basis elements Vi. Furthermore, since the vectors Vi form a basis, they could be used to express the target vectors v tildes. The complex numbers Aij are the components of vector Vj tilde in this basis. We can then substitute this into the Ket-bra representation of A. This will give us operator A completely in terms of the basis elements Vij. From this expression, one could get a matrix representation of A. What do we mean by that? Notice that if A is sandwiched between the bracket Vi and Vj by the orthonormality of the basis, we obtain the equation. We claim that Aij is the matrix representation of A. This is not simply because Aij is a matrix, but something deeper. The left-hand side of this equation actually allows us to represent the action of operator A on a vector as a matrix multiplication. Here's how it works. Our main tool will be the completeness relation derived earlier. This is sometimes called the resolution of identity, because it resolves the identity operator in a chosen basis. For example, let's look at A acting on a vector psi. If we introduce the resolution of identity on either side of A, the resulting vector psi tilde will be given by, where its components are just the matrix representation of A multiplied by the components of psi, which is precisely the matrix representation of the action of A on psi. Similarly, we can also find the matrix representation of consecutive applications of operators. For example, A is the result of the action of C followed by B. Inserting the resolution of identity and identifying the matrix elements, we again get the matrix relation of A equals to B times C. In this way, it is always possible to find matrix representations of operators and vectors, and so, often in literature, it is implicitly assumed that operators are matrices, and vectors are rows or columns. Next, we ask, what is the matrix representation of A dagger? First, start with the matrix Aij, which is equal to the bracket of operator A with respect to Vi and Vj. By the definition of operator Hermitian conjugation, A can be moved to the bra side by putting in a dagger. Then by the sesquilinear property of the inner product, the bracket could be flipped with a complex conjugation. We immediately notice that the bracket under the star is the Ji element of A dagger, and we end up with A dagger Ji star. This implies that the matrix element of A dagger is equal to the corresponding element of A transposed, followed by a complex conjugation. Recall that we simply flip the indices when taking the transpose of a matrix. Hence, in the matrix representation, Hermitian conjugation is equal to the composition of transpose and complex conjugation. We now provide more examples of the operation of Hermitian conjugation viewed from various perspectives. This would be very useful when doing actual calculations. Just remember that it is essentially a way to move an operator from the ket side to the bra side of an inner product. The first example is A acting on psi to give psi tilde. The Hermitian conjugation of this equation is given by. We can evaluate this in the matrix representation, so Hermitian conjugation is just transpose and complex conjugation. Recall that in matrix algebra, the transpose reverses the order of multiplications. This gives the result. Therefore, we get this simple rule for the Hermitian conjugation of the action of an operator on a ket. Note that an operator always acts on a ket to give another ket, and on a bra to give another bra. Next, we look at the Hermitian conjugate of products of operators. We could then use the matrix representation to express Hermitian conjugation. Again, the ordering of the operators are reversed due to the transpose. In general, this works for any sequence of operators and is an often used relation. Finally, let's look at the Hermitian conjugation of a typical Ket-bra. Alpha here is just a complex number. Using the matrix representation again, the transpose switches column and row. In the end, the Hermitian conjugation just switches bras and kets, while complex numbers are complex conjugated. Hence, we obtain a simple rule that is very useful for taking Hermitian conjugations of the Ket-bra representations of operators. When talking about operators in vector spaces, one often talked about their eigenvectors and eigenvalues. These terms fall under the topic of linear algebra and can be found in all standard textbooks on the subject. Wikipedia is also a good reference. Here we will develop it just enough to apply to quantum mechanics. Suppose an operator A acts on a vector A and gives back the same vector multiplied by a complex number A. We call this vector an eigenvector of operator A if it is not a null vector and the number its eigenvalue. This equation is called an eigenvector or eigenvalue equation. Note that A may or may not be a Hermitian operator. We now go through a simple example to illustrate the concepts of eigenvectors and eigenvalues of an operator. A two-level system, where there are only two elements in any basis, should serve our purpose. The operator we have in mind is the Pauli operator, which was invented by the great physicist Wolfgang Pauli to describe electron spin. Sigma x represents the component of spin along the x-axis. The exact details are not important to us presently, and we shall have a lot to say about spin in a later video. We have defined this operator in the Ket-bra representation in the 1-2 orthonormal basis. The state 1 and 2 themselves represents definite outcomes when some observable is measured. We shall only say that this observable is the component of spin along the z-axis. What this means exactly will be explained later in this course. From this Ket-bra representation, one can see that sigma x acts on state 2 to give state 1 and vice versa. It is also apparent that sigma x is Hermitian. The matrix representation of sigma x is given by where the rows and columns are labeled by states 1 and 2. This is called a Pauli matrix and is actually one of 3 matrices, one for each spatial axis. The matrix elements are obtained using the bracket prescription derived earlier. We now proceed to solve the eigenvector equation, that is, find all the eigenvalues and eigenvectors of sigma x. Rearranging this equation, we have where the identity operator is included with the eigenvalue A. Inverting this equation, we should have where the inverse matrix is given by 1 over the determinant of the original matrix multiplied by another matrix, which details are not important here. The inverse of a matrix comes from a standard formula in matrix algebra. You can find out more about it on Wikipedia. The key point is that this inverse doesn't exist because multiplying any matrix with a null vector must give another null vector and can never give a non-trivial vector like A. This implies that the determinant in the denominator of our inverse matrix must be equal to 0. This is due to the fact that the matrix that comes with the inverse is finite and well-defined. This determinant equation will help us find the eigenvalues A, while the corresponding eigenvectors can be found through the vector equation. Let's find the eigenvalues of sigma x using the determinant equation. Using the matrix representation of sigma x, we can evaluate this determinant explicitly. This gives the quadratic equation. Solving this will give 2 solutions, the eigenvalues plus 1 or minus 1. Each of these correspond to their respective eigenvectors, the plus state or the minus state. Expressing the plus state in the 1-2 basis, we have, which can be represented by the column with entries alpha 1 and 2. Finding these complex numbers will give us the plus state. The minus state can be treated in the same manner. Let's find the plus state using the eigenvector equation. The plus state can be represented as bringing out a normalizing factor n, we have a column with 1 as the upper entry and alpha as the lower entry. Since the eigenvector equation constrains the vector only up to a constant prefactor, solving for alpha will give us the plus state, while n can be used to fix the normalization of the plus state to 1. This fixes the absolute value of n. But since the overall phase factor of a state is unphysical, as it doesn't affect measurement probabilities, we can simply set n to its absolute value. Substituting the column representing the plus state into the eigenvector equation and using the Pauli matrix, we obtain the following equation. This leads only to one independent equation, which gives us alpha equals 1. Putting together all the results, we get the plus state, where the normalizing factor n is 1 over square root 2. This can be written explicitly in the 1-2 basis. Similarly, the minus state can be represented by the column vector. with the eigenvalue equals -1. Substituting these into the eigenvector equation gives alpha equals -1. Therefore, we have the minus state equals the column, which in the 1-2 basis is given by. Let's summarize all our results. Both the plus state and minus state are normalized. They are also orthogonal to each other. Together, they form a new basis, as can be seen by the fact that the original 1-2 vectors can be expressed in terms of the plus-minus states. We can express sigma x in terms of its eigenbasis, in which the operator takes a diagonal form. Note that the eigenvalues are real, which means that sigma x is a Hermitian operator. Using the relations between the new plus-minus basis and the old 1-2 basis, we can show that this is equivalent to the original definition of sigma x in the 1-2 basis. In this example, we notice that sigma x is a Hermitian operator, and it turns out that its eigenvectors form a basis. These are no mere coincidences, but are the results of a more general theorem that we shall prove in the next section. Previously, we have shown how using the basis associated with an observable, its operator representation could be constructed. Due to the orthonormality of the basis, the operator automatically satisfies the eigenvector equation with the basis vectors Ket-bras as the eigenvectors and the associated measured values as eigenvalues. We have also shown that if the eigenvalues are real, the operator A is then Hermitian. We now wish to prove the converse. That is, if an operator is Hermitian, this implies its complete set of eigenvectors form a basis, and can be written in this form. With real eigenvalues Ai's, the eigenbasis thus obtained can then represent a physical observable. Thus Hermitian operators are observables. First, some comments before we proceed with the proof. Generally speaking, if an operator is represented in an arbitrary basis, its matrix will typically contain off-diagonal elements. It may be possible to find some basis called the eigenbasis such that A is diagonal. When expressed in this form, we say that A is diagonalized. This expansion of A is often referred to as a spectral decomposition. Note that only some operators, such as Hermitian operators, have an eigenbasis, and so can be used to represent observables. This explains why in most books on quantum mechanics, Hermitian operators are synonymous with physical observables. But generally speaking, any physical property must be observable, and any observation must have an outcome. So a basis representing all possible outcomes of an observation bears a more fundamental relation to the property being observed. Now let's get on with our proof. Theorem: if an operator A is Hermitian, then its eigenvectors will form a complete basis. Proof: assume that the system lives in an n-dimensional Hilbert space. Suppose the operator A has at least one eigenvector and satisfy this equation with eigenvalue A. Then rearranging this equation and following the arguments used previously in the simple example, we arrive at this determinant equation in which A and the identity are n by n matrices. The subscript n of the identity indicates its dimensionality. The implication is that if there exists a complex number A that satisfies this equation, given the matrix A, then the operator A has at least one eigenvector that corresponds to this number. The determinant in this equation can be expanded out using the matrix elements, and the Leibniz formula. Epsilon is the Levi-Civita symbol and is defined by which is equal to 1 for even permutations of indices, and minus 1 for odd permutations. Otherwise, it is equal to 0 if any of the indices is repeated. Notice that this expression is a polynomial of A with degree n, meaning that the maximum power of A is n. This can be seen from the multiplication of n terms, where each could contribute a factor of A. We denote this polynomial by Pn of A. And so the determinant equation can be written as a polynomial equation. Recall that the fundamental theorem of algebra states that any polynomial of degree n with n greater than 0 has at least one root. This implies that our equation has at least one solution. We can then choose the eigenvector corresponding to this solution to be an element of an orthonormal basis of the n-dimensional Hilbert space. The remaining n-1 elements form a basis for the n-1 dimensional subspace, which is orthogonal to state A. If we multiply the eigenvector equation by the bra of any basis element from this subspace, this leads to the conclusion that the matrix element of operator A with respect to states Vi and A must be 0. This result immediately allows us to calculate the matrix element of operator A with the bracket reversed. Since the operator is Hermitian, this is also equal to, and using the sesquilinear property of the inner product, we obtain, which is also equal to 0 from the previous result. The eigenvector equation also allows us to obtain the diagonal elements of operator A with respect to state A. The fact that A is Hermitian then leads immediately to the conclusion that its eigenvalue A must be real. Together, these three properties of the matrix elements of A allows us to construct its Ket-bra representation. Notice that all the cross terms are missing. This is due to properties 1 and 2. More explicitly, the Ket-bra representation of A is constructed by inserting the resolution of identity in the chosen basis. We see that the terms associated with the matrix elements of cross components dropped out. And what is left is the stated expression. The matrix Aij is related to the V basis elements by the usual relation. This matrix is also Hermitian because the operator A is Hermitian. You can easily verify this using the definition of Hermitian conjugation for the matrix representation. Going back to our proof, we see that operator A can be separated into two non-overlapping parts. We can denote the blue operator by An-1. This is a n-1 dimensional operator because from its definition, it acts only on vectors that live in the subspace spanned by the V states to give some other vectors living in the same subspace. Its action on state A is 0. This operator is also Hermitian, as its matrix is a Hermitian matrix, which was shown earlier. If we enter into the n-1 dimensional subspace spanned by the V states, together with the Hermitian operator An-1, which is basically the representation of A in this subspace, we arrive at the start of the second iteration of our argument, with dimensions reduced by 1. Once again, we can find a solution to the eigenvector equation of An-1 that lives in the subspace spanned by the V states. This is again due to the determinant equation being a polynomial of degree n-1, which by the fundamental theorem of algebra guarantees at least one solution. Note that the determinant equation now involves matrices of dimension n-1 by n-1, as they now represent operators in a n-1 dimensional vector space. This argument of using the fundamental theorem of algebra can be repeated n times until at last when we reach a polynomial of degree 1 and the matrices in the determinant equation are now just numbers. This is then the last iteration. At each level, a new eigenvector of operator A can be abstracted from a subspace that is orthogonal to the previously found eigenvectors, relabeling A and A' with an and an-1. We have a set of n vectors that satisfy the eigenvector equation of operator A, which are mutually orthogonal. Therefore, we can conclude that the eigenvectors of a Hermitian operator form an orthonormal basis. As a result, A can be expressed in the diagonal form. This is an important theorem, and much of the calculations in quantum mechanics involve solving for the eigenvectors and eigenvalues of Hermitian operators, which represent physical observables. We now introduce the idea of commutators. This will turn out to be very important later when we talk about quantization conditions and symmetry transformations. A commutator between two operators, A and B, is defined as the following. It is the difference between two different orderings of two operators. The commutator between operators is typically not zero, unlike C numbers, which refer to classical or ordinary numbers for which the order of multiplication does not matter. You can think of this in terms of products between matrices. The result of a commutator is some other operator acting in the same Hilbert space, which could also be just a number. An identity immediately follows from this definition of the commutator. This is known as the Jacobi identity and shows up in many places in physics where the ordering of operations matters. Notice that this is an example of a commutator nested within another commutator, and the ordering of operators within each term undergoes cyclic permutation from term to term. You can easily verify this identity by just expanding the expression using the definition of the commutator, while being careful at each step to preserve the ordering of operators. Another useful identity that follows from this definition is this. It is the commutator of operator C with the product of A and B. Notice that the commutator is brought into the product from the left and distributed to A and B while preserving their ordering. This is very similar to the product rule when evaluating derivatives. Therefore, we call this the product rule. Try to verify this as an exercise. Just substitute the definition of the commutator. Again, take care to preserve the ordering of operators. We will see that this analogy with derivatives is actually more explicit when we discuss the position and momentum operators in the next video. The product rule can be immediately generalized to the products of any number of operators. The proof is simple. Just divide the total product into part A and part B and make repeated use of the product rule. We now introduce another important theorem. If A and B are Hermitian operators, and their commutator is zero, that is, they commute, then there exists a set of states AB over all distinct values of A and B, which forms a basis, and are the eigenstates of both operators A and B, which means both operators can be simultaneously diagonalized in this basis. Let's prove this theorem. To begin, we will start with the eigenstates of A. Suppose apart from A, the state possesses other properties for its full description. We can label these missing information by an additional quantum number, I. Thus we obtain a basis consisting of states AI labeled by all distinct values of the quantum numbers A and I. Since the elements in this basis are already eigenstates of operator A, the Ket-bra representation of A in this basis would automatically be diagonal. At the same time, we would also have the resolution of identity, which would be important for our proof. Since A is already diagonalized, let's look at operator B. Its matrix elements in the complete basis is given by. We can multiply this by eigenvalue A, which is equivalent to inserting the operator A on the left side of B acting on the bra AI. Since A and B commute, we can move A past B to act on the ket A prime J, which will bring out the eigenvalue A prime. Rearranging this equation, we can conclude that the matrix element of B is given by and is only non-zero when A is equal to A prime, as indicated by the Kronecker delta. This will be important in the next step of our proof. Let's expand B by inserting the resolution of identity derived earlier. We obtain the following Ket-bra representation. Notice that the matrix element of B is diagonal in A. This is due to the previous result. So A prime is equal to A, and we only need to sum over A. Therefore, this matrix element can be denoted by B of A ij. From its definition, one concludes that this is a Hermitian matrix, because B is a Hermitian operator. This implies that the operator B of A is a Hermitian operator, which is apparent from its Ket-bra representation. From the theorem proven earlier, since B of A is Hermitian, there exists a basis with states AB that diagonalize it for a fixed value of A with eigenvalues B. This basis is as good as the original basis, and both can equally well be used to express any eigenstate with fixed A. The space of all such vectors is known as the degenerate subspace of A. It encodes all the possible ways a state could have such an eigenvalue with respect to operator A. Whenever an eigenvalue has more than one basis vector in its degenerate subspace, we say that the eigenvalue is degenerate. Therefore, the resolution of identity in this degenerate subspace is given by, which can be resolved in two ways corresponding to each basis. Of course, there are infinitely many ways to do this, corresponding to as many different bases. This, when summed over all values of A, gives back the identity operator for the entire state space, as it should. This operator behaves exactly like the projector into the subspace A. It acts like the identity operator on any vector within the subspace, and eliminates vectors that are orthogonal to it. We can then use this identity to write operator A as the sum of projectors into subspaces A multiplied by eigenvalues A, which is equal to the diagonal form. Similarly, we can write operator B as the sum over B of A in its diagonal form in all the subspaces A, which gives. Hence both operators are simultaneously diagonalized by the AB basis. We derive these from the assumptions of A and B being Hermitian, and that they commute with each other. This concludes our proof. This is an important theorem in quantum mechanics because it encompasses what it means to specify a quantum state completely. For comparison, let's look at what it means to completely specify the state of a classical system. As an example, take a system of m particles. Assuming that these particles have no internal structure, then the state of each particle at any given moment can be completely specified by its position and momentum, and the complete description of m particles would just be the collection of all these information. The dimension of the system is the total number of variables necessary to specify it, which in this case is 6m, 6 variables of position and momentum for each particle in 3 spatial dimensions. All these variables can be known and specified simultaneously. This is the key point. In a classical system, all information that could be known at a given moment can be known simultaneously. Let's compare this with a quantum system. We could describe a state by one of its properties represented by the Hermitian operator A1 in terms of its eigenvalue. Suppose there are still some information missing about the state, and the eigenvalue A1 is degenerate. This implies that the dimensionality of the full Hilbert space N is greater than NA1, which is the number of distinct values of A1. This means more variables are needed to describe the state. Therefore, we add another variable A2 and use its eigenvalues to break the degeneracy of A1. By the last theorem, the operators A1 and A2 must commute in order for a state to be simultaneously an eigenstate for both of them. Suppose even with this added variable, there are still missing information about the state A1, A2, that is, the dimension of the full Hilbert space is still greater than NA1 times NA2, which is the total number of states labeled by these two quantum numbers. Then we will need another variable to break the degeneracy of these two variables, thus A3 is introduced. Again, this Hermitian operator A3 would have to commute with the previous two operators for a state to be simultaneously the eigenstates of all three operators. We could carry on with this program and keep on adding new commuting variables until finally when we reach a set of eigenvalues that is non-degenerate and could uniquely specify a state without needing any further information. At this point, the dimension of the full Hilbert space would then be equal to the total number of states labeled by these eigenvalues. Together, these eigenstates form a complete basis in the full Hilbert space. In literature, the set of operators A, which eigenstates allow us to completely describe a quantum state, is referred to as the complete set of commuting operators. No more operators, which commute with the rest, could be added to this list. We can compare these fully described quantum states with its classical analog. For the quantum case, the set of variables that describe it corresponds to a set of carefully chosen operators, which must commute with each other. Whereas for the classical case, these variables automatically commute as they are represented by just ordinary numbers. Although we can choose to describe the system using alternative set of variables in both the classical and quantum case, there are distinct differences between them. In the classical case, choosing different variables amounts to a coordinates transformation. That is to say, they are physically equivalent, and both sets of coordinates describe the same state. Similarly, for the quantum case, we can also fully describe the state with a new set of variables, B. Again, These new variables will have to be mutually commuting. But the key difference is that the new variables will not mutually commute with the old ones if they are inequivalent operators, unlike the ordinary numbers that describe variables for the classical case. Which means that the old and the new eigenstates are not physically equivalent, like in the classical case. But nevertheless, as a set, both form complete basis that covers the full Hilbert space. Actually, we have already seen something similar in vector analysis. Two different vector bases could equally well describe a vector space, but their basis elements are different vectors pointing in different directions. We have reached the end of this video. This concludes Chapter 3, Part 1 of Weinberg's book on quantum mechanics. If you find this video helpful, consider giving it a like and subscribe to this channel so that you can follow along as we go through the whole book. See you next time, and thanks for watching.